Hello and welcome to another lecture on three-dimensional geometry. Today we shall be starting with the line of shortest distance. Later we are going to find the shortest distance between two non-parallel lines. After that we are going to evaluate the value of the distance between two given parallel lines. And finally we shall conclude this lecture by discussing some numerical problems that would be based on finding the distance between two parallel or non-parallel lines. So now starting with the basic definition or meaning of a line of shortest distance. If we consider line L1 and L2 that are skew lines, that is which are neither parallel nor intersecting, then there is only one line which is perpendicular to both the lines, that is L1 and L2, and this line is known as the line of shortest distance. Next we are going to define the shortest distance between two lines. For that we consider lines L1 and L2 as shown, and MN be a line which intersects these lines, that means L1 and L2, at right angles at M and N respectively. Then the distance MN is known as the shortest distance between two lines, that is L1 and L2 here. Next we are going to evaluate the value of the shortest distance between two non-parallel lines. For that, let the two given non-parallel lines are L1 and L2, whose positional vectors are given as vector R equal to vector A plus lambda vector B, and for L2 we have vector as R equal to vector A2 plus mu vector B2, where lambda and mu represent real numbers and are known as parameters. Let A1 and A2 be 2 points with position vectors A1 and A2 respectively, so that A1 lies on L1 and A2 lies on line L2. Let MN be the line which intersect these lines at right angles at point M and N respectively. Then the distance MN, which is, let's say, equal to D, is the shortest distance between the given lines, that is L1 and L2, and is equal to the magnitude of the projection of the vector A1 A2 along the direction of the shortest distance vector, that is along the vector which is perpendicular to both B1 and B2. Now we know that since the cross product of vector B1 and B2, that is B1 vector B1 into vector B2, is perpendicular to both B1 and B2, which implies that D, which is the distance between the two non-parallel lines, is equal to the modulus of projection of vector A1 A2 along the cross product of B1 and B2. Thus, the value of D can be rewritten as the mod of A2 minus A1 into dot product of vector B1 into vector B2. This divided by the mod of the cross product of vector B1 and vector B2. Since vector A1 A2 is equal to position vector of A2, which is A2, minus position vector of A1, which is A1. and thus we have this vector equal to a2 vector minus a1 vector. Thus we have obtained the value of the shortest distance between two non-parallel lines. Next we are going to consider the distance between two parallel lines. For this we consider two parallel lines which are L1 and L2, and their position vectors are given as: for L1 r vector equal to a vector plus lambda b vector, and for line L2 the position vector is given as a2 plus mu b, where lambda and mu are real numbers or parameters. In the given figure, let a1 and a2 be the points with position vectors a1 and a2 respectively, so that a1 lies on line L1 and a2 lies on line L2. Now let n be the foot of the perpendicular from a2 to L1. Then the distance between these lines would be equal to, let's say, d. Now we have the cross product of vector b and a1 a2 equal to mod of b vector into mod of vector a1 a2 sine of theta into unit vector n cap. Now here theta is the angle between the vectors b and vector a1 a2, and n cap is the unit vector perpendicular to the plane of lines L1 and L2, which means that the cross product of vector b and a2 minus a1 vectors is equal to mod of b vector into mod of vector a1 a2 into sine theta and unit vector n cap perpendicular to lines L1 and L2. This is equal to mod of vector b into a2 n and unit vector n cap. Now since we have assumed the value of a2 n equal to d, therefore this is equal to mod of vector b into d into unit vector n. This implies that the mod of cross product of vector b and a2 minus a1 is equal to mod of vector b into d into 1. Since the mod of unit vector n cap is equal to 1. Therefore, the distance between the given parallel lines, which is assumed to be d, is equal to the ratio of the mod of cross product of vector b and vector a2 minus a1 divided by mod of vector b. Thus, the distance between two parallel lines is given as specified in equation number 1. Next, we are going to consider a problem which states that find the shortest distance between two lines whose vector equations are vector r equal to I plus 2j minus 4k plus lambda into 2y plus 3j plus 6k, and another position vector r vector is equal to 3i plus 3j minus 5k plus mu minus 2i plus 3j plus 8k. Now comparing these given equations with equations that we have discussed earlier in this lecture, where position vector r is equal to a1 plus lambda v1 and position vector for another line is equal to a2 plus mu b2, where lambda and mu are real numbers. Now comparing these two equations, we have the value of vector a1 as I plus 2j minus 4k, vector b1 is equal to 2y plus 3j plus 6k. Similarly, comparing the second equation with this equation, we have the value of a2 as 3i plus 3j minus 5k, and vector b2 is equal to minus 2i plus 3j plus 8k. Therefore, the value of vector a2 minus a1 is equal to 2i plus j minus k. Next we are going to evaluate the value of b1 into b2, that is the cross product of vector b1 and b2. Now in form of its components we can write the vector product as the first row consisting of I, j and k, which are unit vectors. The second row has the elements of vector b1, which are 2, 3 and 6. Row 3 has the elements of b2, which are -2, 3, 8, which is equal to 6i minus 28j plus 12k. Mod of vector product of b1 and b2 is equal to root of 6 square plus minus 28 square plus 12 square, which is equal to root of 964, which can be rewritten as 2 root of 241. Also the scalar product of a2 minus a1 and vector b1 minus b2 is equal to the sum of product of 2 and 6, 1 and minus 28 and minus 1 and 12, which is equal to minus 28. Therefore, the shortest distance between the given lines, which is equal to d, is equal to mod of scalar product of a2 minus a1 and b1 minus b2 divided by the modulus of the vector product of b1 and b2, which is as evaluated is equal to mod of minus 28 divided by 2 root of 241, which is further rewritten as 14 divided by root of 241. With this we conclude this lecture based on the shortest distance measurement of two given lines, which are given as L1 and L2, and their position vectors are R vector equal to A1 plus lambda B1, and for L2 we have position vector as A2 plus mu B2, where lambda and mu are real